Yeah, it's actually going to be, yeah, we'll talk about it. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Good, good. Yeah, hopefully everyone's dealing with this well. So welcome everyone on Zoom as well. Okay. So I've been thinking about this, and like I don't think the iPad thing is ideal, but I like this idea of of having like a virtual component and an in-person component too. And so even after all this is over, I might continue doing this because it's nice, and and the recordings will always be there, and so you can always view them later on. And I think there's just a lot of nice aspects to this. So I just have to come up with a better kind of writing situation here, and I think it'll work out pretty well. Okay. Okay. And so today, what I wanted to do today was I wanted to go over kind of a review of mechanics and strength materials. Okay. So I've never done this before in this kind of class, and so I've taught finite elements before, and I've kind of just always assumed that you guys had a firm grasp of structural mechanics and strength materials, but I thought it would be kind of a good thing to go over it. Another reason for that is I kind of wrote these notes for another class. I said, might as well kind of double dip this and present it for this class as well. Okay. And so actually, if you're coming from EGME 441, which is where I just came from, this will be kind of the sequel to the lecture that you just saw. And so you're going to see this one today, and you're probably going to see the exact same thing next week as well. And so, I'm kind of reusing stuff here, but I think a lot of these same concepts will apply here too. And I think it'll give us a lot of really good context too, because it's, because like you guys have experienced with ANSYS, is that you can put in a situation, you can put in a problem into ANSYS, and it can give you your results, right? But it's still up to you to interpret the results, right? So ANSYS isn't going to tell you how to design your thing, or it's not going to tell you, what to actually do with the finite element results, right? So that still requires some engineering, some conceptual information, right? And so I thought it'd be a good idea to spend, maybe one class session and a half kind of reviewing these concepts, just so that we can interpret the results a little bit easier. And a lot of these concepts will actually give us some good intuition for how do we check to see if our finite element results are actually valid as well. Okay. And so, knowing the background information for the thing that you're studying is always kind of a good idea. And so I thought I'd use this sort of stuff. Okay. All right. So one announcement I want to make is that, Monday is a holiday. So Monday is Labor Day. And so there's not going to be any class on Monday. And so if you come here either virtually or in person, no one's going to be here. And so the door will probably be locked. You'll be by yourself in the Zoom room. And so, you can save yourself that and just, enjoy your day off. Okay. And so the next time after today, the next time we're going to meet is next Wednesday. And I believe that day is going to be an ANSYS day. And so next Wednesday, we're going to do our next ANSYS activity, which is going to be an analysis on a bike crank. Okay. All right. So any questions? Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started.
I have one actually.
Oh yeah.
The assignment that's due on Friday, the intro and activity, how do you want us to turn that in terms of format?
Yeah. No, it's a good question. So so for any ANSYS activity, I don't need your ANSYS files, and so you don't need to upload those. And so all I want is just kind of a document which answers all the questions. And so if you kind of read at the end of the document, I say, please show a screenshot of this, this, and this. And so if you just put a document together that shows all those screenshots, all together in a row.
Like a PDF?
Yeah, PDF. Yeah.
Okay.
And so you'll have a lot. And so I think someone told me that there's like over 20 screenshots that you have to do. And so if you can organize that into a document, and then there's some conceptual questions I want you to answer as well.
And so just like write those out and answer them under.
Exactly. Yeah. So that would be the best thing. So so in the past, what people have done is they've uploaded like 25 different JPEG files onto Canvas, which is fine, but I have to kind of click every single one to kind of view it, which kind of seems like a first world problem. But if you kind of multiply 25 JPEG files that I have to click and load, multiplied by the 35 students that are here, it gets a little bit difficult. It's a little bit easier just to scroll through a document. So if you can put it all into one, it would save me a lot of trouble in grading these things. Okay, and so let's jump into the topic for the lecture today. Okay, and so the topic for the lecture today is we're going to do a review of strength and materials. Okay. And so what is strength and materials? And so strength and materials, hopefully it's a class that you guys have all had before at some point in your life, okay? Whether it be, something recent, or maybe it's something that you took, when you did your undergrad, many years ago. But the way I think of strength and materials is it's a discipline of study that tells you how a material or how a structure will deform in response to external loads, okay? Okay. And the way that objects kind of respond to external loads depends a lot on the material that it's made out of. Right. And so intuitively, I think we can all kind of picture this. Right? And so if you take like a rod, and so let's say the rod is made of some kind of metal, so let's say structural steel, and you try to bend it, okay? Unless you're like have some Olympic level strength, you're not really going to do much of that rod, because we know steel is really, really strong. Okay. But if you take a rod that's made of something soft, like maybe like rubber, right? Then you're going to take the rod and you're going to bend it with no problems, right? And so the material and what it's made out of has a really big impact on how these structures deform, right? And the way that we kind of differentiate between different materials is through its material properties, okay? And so things like its Young's modulus, things like its density, things like its Poisson's ratio, okay? And the way that these parameters kind of interact with external forces, that's the whole area of strength in materials, or at least the way that I kind of interpret it. Okay. As an aside, it's funny that I'm kind of giving these lectures because I definitely don't consider myself a structures guy, and so I'm definitely much more a fluids and thermal person. So I was putting together a lot of the notes for this semester. It's like, wow, I have this class, I have biomechanics, I have another finite element class. Like, man, I've turned into a structures guy. But that's just kind of how the cookie crumbles, I guess. Okay, and so let's start with just the basic concept of a stress. Okay. And so we've all seen stress, in our first ANSYS activity, right? And so, you perform that analysis within ANSYS, and then what you were able to obtain was things like how the equivalent stress is distributed within the object. Okay, and so let's talk a little bit about what that actually means and why stress actually develops in these objects. Okay. All right, so let's start with its units, okay, or its dimensions. And so stress is nothing more than just a force that's distributed over an area. Okay. And so the units for it are exactly that. And so it's just going to be force over area. Okay. And so the symbol that I give for stress is often a sigma. Okay. Okay. And then the dimensions for sigma are going to be a force over an area. Okay. If we put some units on this, go away. If we put some units on this, it's going to be something like newtons over meter square. Okay. And so this has a special name. And so the person who came up with the brilliant idea of putting force over area, his name was Pascal. And so we'll call it by its appropriate name. Okay. Okay. And so the SI unit for stress is Pascal. Okay. Question? Okay. And so, what you'll notice is that, the units for stress are the exact same units for pressure, right? Okay. Right. And so pressure is also a force that's distributed over an area, okay? And it also has units of Pascal. Right? And so, even though like physically stress and pressure are the exact same thing, we use them under slightly different contexts, okay? And so let's talk about pressure first, right? Because we actually used a pressure too. And so in our first ANSYS activity, we used a pressure force on the side of the plate. Right? Okay. All right, so pressure, it's a force over area, but a pressure is usually something that's applied externally to an object, okay? Okay. And so a pressure force is, or a pressure, force over area is something that's applied externally that causes the object to respond, okay? And so kind of the analogy that I gave in my last class in biomechanics is that you can think of pressure as something that your professor applies onto you by making you do assignments and projects and exams, things like that, right? And so it's something that's applied externally to, what you're examining, okay? Okay. And that's reflected in, you know, in the boundary conditions that we can apply in ANSYS too, right? And so remember, you know, we talked about on Monday that boundary conditions are something that you apply externally to your object, right? And one of the boundary conditions that you can do is a pressure, right? So that kind of lines up with this definition. Stress, on the other hand, you know, even though it has the same dimensions as pressure, stress is something that develops internally inside an object in order for it to maintain, you know, some form of equilibrium. Okay. And so stress is something that develops naturally within the material. And it's a function of the material properties that we talked about before. So things like the Young's modulus and the Poisson's ratio. Okay. And it's something that an object has to do in order for it to maintain, you know, equilibrium with its surrounding environments. Okay. And so, you know, keeping up the same comparison that I started with, you know, you can say that stress is something that develops inside students as a response to, you know, the pressures that, you know, that their professors give them. Okay. Right. And so it's kind of a subtle difference in between the two, right? And so even though physically they're the same thing, and so you can both say that they're a force that's over an area, but the context in which we use to describe them are different. Okay. And so if you think back to our first ANSYS activity, right? And so the stress field that we were viewing in that plate with the hole, that was developed inside the object in response to the loads and constraints that we placed on it. Okay. Okay. Any questions on this so far? Okay. All right. And so let's do kind of a simple example just to kind of show you, you know, kind of illustrate this concept of stress, right? And so let's think of a rod. Let's think of a rod that's in tension. Right, so here we have a rod. Let's say that we're pulling on it on both sides with some tension T. Okay. Right. And since, you know, we're pulling on the rod with the same force on both sides, you know, we can say that this rod is in equilibrium, right? And so it's not going to move, it's just going to stay there. And so what we can say is that, you know, not only can we say that this rod is in equilibrium, we can say that every single part of this rod will also be in equilibrium. Okay. And I mean every single part, right? And so if we take a slice, and so let's say we take a slice of the rod like right there, okay? Okay. Whereas on the left-hand side, we have a tension T, okay? If we say that every single part of this rod is in equilibrium, that means this part of the rod must also be in equilibrium, right? And so in order for it to be in equilibrium, we have to have some kind of internal forces or some kind of internal stress that develops on this cross-section in order to maintain that equilibrium, okay? Okay. And so we'll call that internal stress sigma, okay? And so if we make a force balance here, or let's say let's balance the forces on this diagram. Okay. And so on the one hand, we have the internal forces, right? And so we have the internal stress sigma, okay? And if we want to transform that into a force, we have to multiply it by A, which is the cross-sectional area. Okay. In order to have static equilibrium, then the product of sigma times A has to be equal to the tension T, right? Okay. And so we can take this expression here and solve for sigma in this very simple case, right? And so we can say that sigma is equal to T divided by area. Okay. Right. So very, very simple. Okay. All right. And so I think, a fair question to ask is, in the end, we want to take this segment here and we want to maintain equilibrium here, right? And so there's lots of different ways that we can do it. So why don't we just apply just another force T that's right here, okay? Right. So why do we have to bother distributing it over the area, right? And the reason for that is, because we're applying this force T right here, okay? And our specimen here, or our rod, has some kind of thickness, it has some kind of area. It doesn't make sense for all that force to be internally concentrated on one particular region or the other, okay? And so that force actually gets distributed throughout this entire structure, right? And so that's kind of exactly what the stress represents, right? So the stress represents that any kind of internal or any kind of external load or any kind of external force that you place on a structure, that naturally kind of gets distributed over, over an area of your object. Okay. All right. Any questions on this? Okay. All right. And so now that we kind of, we understand kind of the concept of stresses and kind of why they develop and what they are, let's go over the different kinds of stresses that we can see inside a structure. Okay. Okay. All right, and so for the first type of stress that we'll go over is the normal stress. Okay. And so normal stress acts perpendicularly to a surface. Okay. And so the stress that we saw on the previous page, that was a normal stress because it acted perpendicularly to the surface. Okay. Okay. On the other hand, we have shear stresses, and shear stresses will act parallel to the surface. Okay. All right, and so if you want to draw an image here, okay. A normal stress will act like this, okay? And so here we have a compressive normal stress. Whereas if we draw a shear stress, it would look like this, it would act parallel. Okay. And so you can have both kinds of stresses that are active inside your structure at the same time. Okay? In fact, we have these two different kinds of stresses, and they can also act in different directions as well. Okay. Okay. And so by directions, what I mean is the Cartesian directions. Okay. All right, and so let me draw a cube here, okay? And so this will kind of serve as the basis for our discussion. Okay. Right, and so if we take kind of an arbitrary cube outside of any structure that's undergoing stress, what we can say is that we have on every single surface of this cube, we're going to have normal stresses and shear stresses acting on every face. Okay. And so first, let me draw the normal stresses. Okay. And so I'm just going to draw the faces of the cube that are in the foreground, but you can imagine that there's the exact same stresses that are occurring on all the other faces as well. Okay. And then we also have the shear stresses as well. Okay. And so the normal stresses are going to be normal to the surfaces of this cube, and the shear stresses are going to be parallel to the surfaces. Okay? And in fact, we can actually characterize all the different stresses on this cube using a stress tensor or a stress matrix. Okay, and we can characterize and we can kind of label each of those stress components. Okay? And so in reality, for any kind of arbitrary structure, any kind of arbitrary stress state, we can say that there are 6 unique components of the stress. Okay. And so there's going to be 3 normal components. Okay. And so 3 of 6 of those will be normal stresses. And then 3 out of those 6 are going to be shear stresses. Okay. And so on the next page, I'll describe what each of those stresses look like, what their symbols are, and how you can interpret them. Okay. And also, we'll go over what they actually mean for, for the stresses that you see on ANSYS, right? Because stress is actually a complicated thing. Because stress, the way, if you want to give a formal definition of it, it actually is defined often in terms of a matrix or a tensor. Okay? But in ANSYS, we're not viewing a tensor, and so what we're viewing on ANSYS is just kind of a single quantity, right? And so all you see in ANSYS is just a heat map of stresses, right? And those stresses kind of just represent a single value, right? And so how do we get from a matrix quantity into a scalar? It's something we'll talk about on the next page as well. All right. So before we do that, are there any questions on this? Okay. All right, so let's go over the 6 components of stress. All right, so let's go over the 3 normal components first, because I think that's kind of the easiest ones to do. Okay, and so remember, normal stresses are going to be perpendicular to the surface. Okay, and so we're going to have a normal stress in the x direction, one in the y direction, and one in the z direction. Okay, so these are normal stresses. In the x, y, and z directions. Okay. Right, and so you'll notice I put each of those directions twice on those, right? And so I do sigma x, sigma y, sigma z, right? That's not because I'm weird. It's because it's to kind of differentiate them from the shear stresses. Okay. And that double notation will make sense once we start talking about the shear stresses, okay? Oops, that's not a tau, that's a j. Tau xy, comma tau yx. Okay, and so actually all the shear stresses here will come in pairs, okay? Because these pairs are equivalent to each other. Okay? Okay. And so all of these are shear stresses. Okay. And the way that you read these off is that you take both letters in into consideration. Okay. And so the first letter or the first direction okay. And so the first direction will just simply tell you which direction the stress vector is pointing. Okay. Whereas the second letter that you see in this notation here, okay, the second direction will tell you on which plane that it's acting on. Okay. All right, so as an example, let's take tau xy. Actually, let's do tau yx, okay? right? And so what this tells us that this stress here is going to be it's going to be applied in the y direction, right? And so this stress component is going to go vertically like this in the y direction, okay? Okay. And then the second letter there will tell us, you know, it's going to be acting on a surface that's perpendicular to the x-axis. Okay. And so if we draw a surface, and so we say that the x direction here is our normal vector, okay? And so if we draw a surface that's perpendicular to that, which is very hard to do on a 2D surface, okay? But you can imagine that, you know, this surface here, you know, part of it's coming out of the page and going into the page, whereas the x, you know, the x-axis here, and so the x direction, this is perpendicular to it, okay? Right? And so the x direction, so the x letter here will determine, you know, which way the surface is facing, okay? And then the y direction will tell you which direction the stress is actually pointing, okay? And so tau yx here is a stress that points in the y direction that's on a surface that's perpendicular to the x direction, okay? So it's a mouthful, but I think once you kind of get used to the notation, it becomes, you know, a little bit straightforward, okay? Okay, so any questions on this? Okay, all right. And so why did I pair these, right? And so why did I say that tau yx is the same as tau y, or tau xy is the same as tau yx, okay? And the reason for that is, you know, in order to maintain, you know, static equilibrium, right? Okay. In order to maintain static equilibrium, then the shear stress, the kind of the reciprocal shear stress component, or the one where the letters are flipped, those have to be equal, and those have to be equal in magnitude to each other. Okay. Okay. Right. And so you can prove this, and so it's not something I'm coming up out of thin air, and so it's I think it's a proof that's classically done in you know, a strength of materials class, and so, you know, we're not going to prove it here, but, you know, just know that, you know, the once you swap the two values, or once you swap the two letters, that, you know, you get the same thing back, and the reason for that is for static equilibrium. Okay. Okay. And so, you know, because the reciprocal shear values, they're the same, in the end, you just end up having 6 unique values here. Okay. Okay. And so we'll consider these to be the 6 unique ones, right? And the way that you kind of sum these up, and the way that you kind of you know, kind of represent them, is in a stress tensor. Okay. And I'll write that on the next page. But before I go there, is there any questions on this, or do you guys need me to stick around here to write stuff down for a little bit? Okay. All right, so let's go over the stress tensor. Have you guys heard the word term tensor before? Do you guys know what that is? Okay, that's good. And so it's just a matrix, okay? Okay, and so the stress tensor is a 3x3 matrix, okay? Okay. And in fact, I think this particular stress tensor is the Cauchy stress tensor. Okay. Okay. And so in this stress tensor, you have all the normal stresses on the main diagonal, and then all the shear stresses are on the off diagonals. Okay. All right, question. So is it similar to the open circle cross product? Oh, are you talking about the what's it called? The outer product. This is something that's different. And so the outer product gives you a way to get a tensor like this. And there's some outer products that actually give you this tensor here, but this is something different than that. Yeah. Mm-hmm. All right. Okay, and so you can see that stress is a complicated thing, right? And so if you kind of think of any arbitrary structure here, okay. So let's say that we have a snake, I guess, right, or a wiggly tube, okay. At every single point on this snake right here, okay, you have a stress tensor, right? Okay, and so each point is going to have its own unique stress tensor that describes the stress state at that point. Because the stress at every different part of an arbitrary structure is going to be different, right? And so if you think back to our activity, right? And so I think a lot of you guys got to the point where you got to see the stress distribution, right? What you saw was that the stress was much higher around the hole, right? And so we have kind of a higher stress concentration around there. Whereas in different parts of the plate, you might have higher and lower stress depending on how close you are to the hole, okay? And so stress is going to vary throughout the entire structure. Because there's going to be different stresses that are needed at different parts in order to maintain equilibrium. Okay? But there's a little bit of a disconnect here because what I'm telling you here is that stress is a complex state, right? And so stress is not really a number. It's kind of more of a tensor quantity, right? But what you're viewing in ANSYS is actually just a single number, right? And so if you think back to what you're seeing in ANSYS, you see a color contour plot, but the colors only represent a single value, right? And so like the red would only represent a stress of something megapascal, right? It might be like 38 megapascal or something like that, okay? And so the question now becomes like what exactly are you viewing in ANSYS, right? And so since we know that stress has six components, are we viewing this one? Are we viewing this one? Are we viewing this one? Okay, right? Are we viewing any of the shear components, right? Okay. So which one are we viewing, right? Because we can't really view all of them at the same time because that would require some weird 4D time distortion, color, weird stuff, right? And so our eyes can only see one color at a time, right? And so the color can only represent one number. And so the question is which stress or what stress are we actually viewing out of the 6 that we know that exist, right? Okay. And so kind of the answer to that question is we're kind of seeing all of them at the same time, right? And so if you remember, when we defined our results for this activity, we defined a very specific name for the stress, right? We didn't call it a normal stress or a shear stress. What we said is we're viewing what's called the equivalent stress. And so the equivalent stress, or another name for this, is the von Mises stress. Okay. Just like many things in science, named after the guys who created it. Okay. And so the von Mises stress it's a scalar quantity, and so it's a scalar expression of the stress that combines these 6 different components. And so what it does actually is it takes the 6 components and it plugs into a formula, and it gives you just one value of stress that kind of combines the contributions from all 6 components. Okay. And so I will give you the formula for that, but I don't have it in these notes. And so I'm going to shamelessly look it up on my phone right now. Not von Miller, von Misa Stress. There we go. Thank you, Google. First thing. Okay. And so on the next page, I'll write down the formula for the von Misa Stress for you, just so that you know that what you're computing in ANSYS, this is actually what you're computing. Okay. But before I do that, are there any questions on this? Okay. All right. So let's write down the formula for the von Mises stress. Okay. I actually spelled his name right, which is amazing. Okay. And so I'll call this stress a sigma E. And so the E here stands for equivalent. Okay. And so it kind of looks similar to a distance formula. Okay. Right. Let me look at this one. Okay. And so actually, no, it's not the one that I want. Sorry about that. Should have prepared for this beforehand. I should have known that we're going to go in this direction for the class today. All right, yeah, that's good enough. Okay, so it's going to be square root of sigma xx squared times minus sigma x sigma y, okay, plus sigma y squared, okay, plus tau xy, 3 tau xy squared, okay? And so this is in 2D, okay? Because this only has x and y components, but we can extend this formula to 3D as well, okay? And so in 3D, this is going to be sigma xx squared minus sigma xx sigma yy, okay, plus sigma yy squared minus sigma, let's do plus sigma zz squared, okay, minus sigma xx sigma zz minus sigma yy sigma zz, okay, plus, and we have all our shear components. We have 3 tau xy squared plus 3 tau xz squared plus 3 tau yz squared. Okay. And all this is under the square root. Okay. Okay. And so it's a complicated expression, right? And so that's why it's kind of hidden from you as the user. But you can see here that the von Mises stress, it includes contributions from all the normal components and all the shear components as well. Right. All right, question. So the question is, how was it deemed to be an accurate equation to convert stress tensor to a scalar as derived from a differential equation? No, that's a good question. And so the question is, how did he come to this equation right here, and how is this deemed as like an accurate representation of the stress state? And the question is that I'm not sure actually, and so I'd have to look at the derivation of this formula and how they determined it, right? But it's it's one that's used a lot in industry for for determining stresses. Okay. Yeah, no, it's interesting. Yeah, anytime you have any kind of a scalar representation of like a vector quantity or a tensor quantity, I think it really begs the question of how do you get there? Okay. Okay. And so, practically speaking, you guys don't actually have to know what this formula is, at least not for this class. Okay. What I want you guys to know is how do we actually use this stress? Okay? And this will be, and we'll touch on this on the next activity, on the activity next week as well. Is that the way that we usually use this equivalent stress is we use that to determine whether or not our structure is going to fail or break. Okay. Right. And the way that we do that is we compare what we compute from the von Misa stress to something called the yield stress or the yield strength of a material. Okay. And so every material out there, or at least every structural material, has a parameter called the yield stress or the yield strength. Okay. And what that tells you is that the yield strength is the maximum amount of stress that the material can take before it just starts to rupture, before it starts to break. Okay. And so what we're going to do in the activity next week is that, I'm going to give you basically a situation where a structure is going to be put under stress, it's going to be put under force, right? And I want you guys to determine, based on the stress that you compute in ANSYS, I want you guys to make a prediction of whether or not the material is going to break or if it's going to hold. Okay. And then based on that results, then you can design your part, a little bit better, right? And so you can either make it so that, if the material is going to break, you can reinforce the material by adding some more volume. Okay. Or if the material is not going to break, then you can improve the design by removing some material to make it more efficient to manufacture. Okay. All right, so a little bit of a sneak preview for next week. Okay, so any questions on this? Okay. All right. And so that's stress. And so stress is a very important concept for for finite elements or just structural mechanics in general. Okay. Now let's go over the concept of strain. All right. And so strain is typically what we use to describe deformations that occur on the interior of a structure. Okay. Right. In terms of units, strain has no units. Okay. Okay. And the reason it doesn't have units is that it's basically a ratio of two different lengths. Okay. Okay. And so it's defined as the change in length of a structure divided by its original length. Okay. And so as an example, let's have a bar like this. Okay. So let's say that this bar has a length L. This is the original length. Okay. Let's say that we're going to pull on this bar with a force P. Okay. And so by doing that, we're going to extend the bar by a certain amount. Okay. Whereas let's say, maybe this was the original length. and this is the amount of length that it increased, okay? And so as a result of the pulling, the length increased by an amount delta L, okay? The strain in this bar is given by, we'll give it the symbol epsilon, okay? Oops. And so epsilon is going to be delta L divided by L, okay? And so it's the change in length divided by the original length. Okay. All right, so that's its definition in the 1D case, but it's this can be generalized to 3D as well, right? And so in 3D, it's just kind of it's a representation for how much is changing in a certain direction, divided by how much how big it was in that originally. Okay. Okay. So any questions on this? Okay. All right. And so, the reason we go over strain is that stress and strain inside a material are often very intimately connected. And oftentimes they depend on each other. Okay. All right. And so kind of the, and we'll go over this more in a little bit, but I just want to introduce this concept for now, okay? And so for a linear material, okay, and I guess we did talk about this a little bit on Monday, okay? Right, and so for a linear material, or basically the materials that we assume when we do static structural, okay, the relationship between stress and strain in material is linear. Okay, and so what we can say is that the stress sigma is equal to E times epsilon. Okay. Or in other words, the stress and strain are linearly related. Okay, and then the factor or the coefficient of linearity is given by E, which is the Young's modulus. Oops. Okay. Right. And so in this simple relationship, what you can see is that the more strain that an object undergoes, the more stress it's going to experience. Okay. And then kind of the proportionality constant in between the two is the Young's modulus. Okay. This area of my iPad's really hard to write on. Okay. And so in order for this equation to hold, then the units for the Young's modulus have to have the same units as the stress, right? And so the units for Young's modulus are always going to be something like in pascals, megapascals, or something like that, okay? Because remember, strain is dimensionless, and so in order for this equation to hold, Young's modulus also has to have units of pascals as well. Okay. All right. So any questions on this? Okay. All right. And so what this looks like in a linear material is something like this, right? And so if we graph it out, and so let's say that on the x-axis here we have strain, and on the y-axis we have stress, okay? Then we're going to have a linear curve like that, okay? Right. And so this right here is linear elasticity. where sigma is equal to E times epsilon. Okay. And remember what we talked about on Monday is that this linear relationship in between stress and strain, this only really holds for a relatively small deformation. Okay. Because once you start to kind of get beyond this and you start to get to higher levels of strain, okay, then the stress that that the material experiences is no longer going to be linear. Okay. And so, a typical stress strain curve might look something like this, where you start with a linear region, okay? But then after the linear region, you start to go nonlinear, okay? And this region right here, this is known as plastic deformation. Okay. And so if you ever, if you're running your finite element simulation and you notice that the deformations look fairly large, right? And so you look at the values for deformation, you say, that looks pretty big compared to my model. You might have to start looking into plastic deformation because if you don't explicitly turn this on, ANSYS is not going to actually account for that for you. And so ANSYS is just going to assume that it's just going to be linear because linear is good, linear is happy, right? And so it's just going to say, we're just going to keep being happy until we reach something up here, okay? And so if you're up in here in this region right here, right, then you're not going to get a very accurate result because actually probably your structure is going to break kind of way before it gets over there, okay? And so you want to watch out for that. And so if you ever start to see kind of large deformations in your model, either you may have made a mistake in setting it up, or if you didn't do that, then you have to make sure you turn on plastic deformation so that you get that right behavior. Okay.
Any downside on just keeping that plastic deformation option on all the time?
Yeah, no, it's a good question. And so the question is there a downside to keeping plastic deformation on? The downside is cost. And so it's a lot more expensive to account for plastic deformation because you no longer have this linear relationship. And so the equations start to get a lot more complicated. And so if you try to solve, if you do kind of a side-by-side comparison, so you solve a situation with plastic deformation on and without, the one with plastic deformation will take a lot longer to solve. And so if you're pretty confident on all the other settings of your simulation, I'd say go for it. But a lot of times when you're running finite elements, you're kind of tinkering with things in lots. You're tinkering with the mesh, you're tinkering with the boundary conditions. And if you have to wait even like 3 or 4 minutes for each simulation because you're trying plastic deformation, that's going to add a lot of time onto your whole analysis. And so, yeah, so you kind of have to be careful of doing that. But if you have a lot of confidence and all the other settings being right, I'd say go for it. Mm-hmm. Okay. Any other questions on this?
Professor?
Yeah.
So I know you said that we want to start looking for plastic deformation at larger deformations. Is there a numerical way to do that? Say, for example, your material rate, say it's like 6.61 P6 for example. You look up your stress strain chart, you find out where the chart turns from linear deformation to plastic, and then you maybe say you run a simulation with non-plastic. You look at the highest stress. If that highest stress is above that turning point, then would it be a good idea to turn on plastic deformation?
Yeah, I'd say so. Yeah, that's a good way to do it. And so if you do have the stress strain information and you have it handy, then you can just check to see what's the maximum stress and did I go past the point of plastic deformation. That's a surefire way to do it. A lot of times you might not have that information or it might not be handy because a lot of times you might be working with like a non-isotropic material. So you might be working with like wood or something like that. And so in those cases, it's after you kind of do it, you kind of do finite elements for a while, you kind of get a feel for it. You kind of get to see, this looks kind of really big for what this object should be. And so, that's how you kind of do it. So the way I kind of do it is I look at kind of the general dimensions for my geometry. I say that, let's take our plate, for example. So the plate is 300 millimeters by 200. And if I'm getting deformations kind of on that same order of magnitude, if I'm getting deformations like 50, 60, 70 millimeters, which is getting pretty close to how big my object actually is, then I would say that's pretty large, and I would have to go turn on plastic deformation to make sure that it's okay. Yeah, good questions though. All right, any other questions on this? Okay. All right, and so far, we've been covering, the stress strain relationship for normal stress, but actually, there's also an analogous stress strain relationship for shear stress. Okay. Oops, let me go back to black. Okay, and so the formula here looks pretty similar. Okay, and so on one hand side, we're going to have the shear stress tau. Okay. Okay, and this is going to be equal to G times lambda, okay, or gamma. I forget my Greek letters. Okay. And so this G here is the shear modulus. Okay. And this gamma right here, this is the shear strain. Okay. And so it looks exactly the same as the linear, as the normal stress components, just that we swapped out all the letters, right? But you can see here that we still have a linear relationship in between all of them. Okay. And the nice thing about this is that if you have an isotropic material, or material that the material properties don't change in either direction, there's a relationship that you can have for the shear modulus, where you can relate it to the Young's modulus and the Poisson's ratio, right? And so for a lot of materials, and this is true for a lot of metals, because metals are pretty isotropic, you can compute the shear modulus by taking the Young's modulus and dividing it by 2 times 1 plus Poisson's ratio. Okay. And so technically, the shear modulus is a different material property for the material, right? But a lot of times you don't have to actually set this. And so you'll see this next week, when we do our activity. And so in the activity next week, I'm going to have you guys create a custom material, okay? But when you create the custom material, even though technically shear modulus is something that ANSYS needs in order to solve the simulation, it's not something that you're going to put in manually, okay? And so manually, the only things you're going to put in are the Young's modulus and the Poisson's ratio right here, okay? And then because we have this formula, ANSYS is going to automatically compute the shear modulus for you based on the Young's modulus and the Poisson's ratio. Okay, but remember, this is only true for isotropic materials. Okay, but it's an important thing. And actually, speaking of the Poisson's ratio, let's go ahead and define that here. Okay, because we've talked about Young's modulus and what that does, and you can see shear modulus here. Okay. But Poisson's ratio is another important quantity that we have to know what it does. Okay. And so Poisson's ratio, symbolically, we usually give it the symbol nu, which is kind of the fancy V, that's what I call it. Okay. And so what the Poisson's ratio does is it measures how much a material will deform in directions that are perpendicular to the loading. Okay. Right. So informally, this is kind of the formal definition, and so I got this from Wikipedia, and so it's reliable. Okay. And so the kind of the informal definition for Poisson's ratio that I can think about is I think of it as kind of like the squeeze or the squish factor. Okay. And so as an example, let's consider our bar again. Okay. And let's say that we're going to put this bar in tension. Okay. And so, since we're pulling this bar in tension, we know it's going to become longer than it is before, okay? But, in order to kind of maintain mass, right, because of conservation of mass, even though this bar is getting longer, right, the bar has to have the same amount of mass as it did from before we started loading, okay? And so if I draw the original geometry on top, it might look something like this, okay? Okay. And so this is highly exaggerated. So you're not going to see a big case like this, okay? But you can see here that in order to pull the material and to kind of stretch it, right? In order for it to actually stretch, it has to get thinner at the same time, right? Because it has to maintain the same amount of mass as it did before, right? And so the Poisson's ratio basically tells you how much the material is going to squeeze, or if it's going to squish it, or because if you compress it, the material is going to get shorter, but then it also gets kind of squishier too. And so that's kind of what the Poisson's ratio tells you is how much that occurs. Okay. And so numerically, the Poisson's ratio is a ratio, and so it's a dimensionless quantity, and it's usually something between, or it's bound to be something in between 0.0 and 0.5. Okay.
There's some materials that do the opposite, right?
What do you mean? Oh,
when you elongate them, they get bigger.
Yes. Yeah, that there are some that do that, but then the way that it does that is it kind of incorporates kind of more air kind of in between.
Right, they're like a mesh type of material.
Exactly. Yes. Yeah. But for like a typical kind of like metal or like a whole solid material, then it kind of does stuff like that.
Like titanium, not titanium, like skins, or they look like skins.
Oh yeah, anything with kind of like a mesh that kind of does that. Yeah. Yeah. So Poisson's ratio will take a value between 0.0 and 0.5. Okay. And so the closer the Poisson's ratio is to 0.5, the more incompressible it is. Okay. And so a lot of solid materials that we'll talk about are kind of closer to the spectrum to 0.5 because we consider them to be incompressible. Okay. But for a lot of engineering materials that are elastic, you can find Poisson's ratio typically in the range of 0.25 to 0.35. Okay. Right. So that's what the Poisson's ratio does. Okay. All right. Any questions on this so far? Okay. All right. So the last thing I want to cover today before we head out is this concept called the Saint Venant's principle. And so how many of you guys have heard of Saint Venant's principle before? Yeah, Jacob did because we just went over it in biomechanics right before this. But it's good. Okay, so it's not something that it's actually not something I learned when I was in college either, and so it's only something that I became familiar with, as I was doing a lot of finite elements. But I think it's a really nice principle to kind of give you some good intuition for how to interpret your finite element results and how to predict what the result should look like. Okay. And so just as kind of a preface to this, all that we've been talking about today is that, when you apply loads onto a structure, we know that there's going to be some stresses that develop. Okay. Okay. I should say external loads and constraints. Okay. Right. And we know that the structures have to do this in order to maintain equilibrium. Okay. Okay. And so as an example, let me do a different example. Let me do a beam, okay? Because I've drawn the same bar so many times today. Okay. Okay. And so let me take let's take this beam where it's going to be fixed on one side, and let's apply a load at the end of it. Okay. So we'll call this a load L. And so, we know from the class today that, because we're applying this load here, and because we're fixing it to the wall, there are some stresses that have to develop within this beam in order for it to maintain static equilibrium, right? And so what St. Venant's principle will tell you is that, near the areas where you're applying external effects, okay, near the areas where you apply external effects, right? Right. This is where, the solutions are going to be the most interesting. Okay. And what I mean by that is this is where you're going to have areas of stress concentration. This is where you're going to have areas of high deformation. Okay. And so basically, wherever you apply the loads or wherever you apply your constraints, that's where you're going to have peaks in your finite element solution. Okay. Right, and so this is really useful in finite elements because this will allow you guys to basically make a prediction for how what the solution is going to look like before you actually do it. Okay, and so for this particular case, I can tell you right now that this area right here, which is where we're fixing the beam to the wall, we're going to have stress concentrated here. Okay. Right. And so near the fixed support, that's where we're going to have a stress concentration. Whereas on the right side, which is where we're applying the load, okay, this is where our highest deformation is going to be. Okay. And so on one end, we have the highest stress, and on the other side, we have the highest deformation, right? And so what do those two locations have in common? That's where we're applying kind of our external effects, right? So that's where we're applying our external support, and that's where we're applying our external load, okay? And so what St. Venant's principle tells you is that, that's generally where you're going to see the most interesting behavior, okay? And then conversely, as you move away or as you move further away from, the parts where you're applying external loads, the solution gets a little bit less interesting. And the whole idea with St. Venant's principle is that, when you have a deformable solid or you have an elastic solid like this, a lot of the deformations or a lot of the effects that you get from applying external loads, they're all local effects, right? And so, just because you're applying a load here on one side of the beam, The rest of the beam is going to feel it, of course, but kind of the effect of that, or kind of the influence of that external effect, kind of decays as you get further and further into the structure, right? Until you get to another part where you have another external effect. Okay. And so it makes it seem kind of fancy, but I think it's intuitively you kind of understand what it is too, right? And so if I take this chalkboard here, right, and I start like hitting the chalkboard, we know that's going to cause some vibrations in the chalkboard. But if you stood over there on that side of the chalkboard and you put your hand on it, you're not going to feel the vibrations of it because you're so far away from where I'm making this vibration here. Okay. And so intuitively, I think that's something that I think a lot of people understand. It's just Saint Bernard kind of put it in words, and he became famous for it. And so this is kind of a nice way to kind of use to kind of check your finite element results. Because if you're far away from like one of the boundary conditions on your model and you see that your stress is really concentrated, you might want to double check that and see if that's really the case, or if that's actually what's happening. But I will say that it's not always as simple as this, because in finite elements you also have a lot of other factors like geometry. Okay. And so, other factors might have a stronger influence on whether you see a stress concentration or not. But this is kind of a good principle to kind of keep in the back of your head to kind of, see, am I seeing the right effect, or is my finite element simulation making sense to me? Okay. All right. Any final questions on this before we wrap up for today? Oh, question here in Zoom. Oh, just laughter. Okay. All right. So that's all we got time for today. So thank you guys for coming. Thank you guys for tuning in. Right. And remember, there's no class on Monday. So don't come here, and don't log in on Zoom, because I won't be there. Okay. And so the next time I see you guys will be next Wednesday. And next Wednesday, we're going to do another ANSYS activity. Right. So hope everyone has a great weekend, and I'll see you guys next week. Yep.
And the assignment part, we need to calculate the maximum stress, right?
Yeah.
So there are two stress, like the total stress, so the principal stress and the equivalent stress. So,
yeah.
Which one? Equivalent stress, like theoretical stress, right?
Yes. Yeah. So use the equivalent stress.
We have to do the
yeah. Yeah.
Second, the tutorial which I followed, it has 1000 megapascal.
Yeah.
In the class you told for
it should be 10,000. It's a typo, but for this assignment, it's just the intro one.
No,
so
just
I
wanted to confirm again.
Yeah. It should be 10,000.
Got it. Thank you very much. Have a good day.
Thanks. See you weekend. See ya. Oh, question. So in the plate with hole, if we cut the plate, there will be more stress internally due to compression and tension. Yes, yeah. And so if you cut the plate in half, you'll be able to see kind of where all the compression and tension kind of takes place there. Yeah. Are you talking about running a different simulation, or are you talking about the simulation that we have, but just kind of cutting it in the middle? Oh yeah. So the plate with the hole is unique because you have the hole that's in the middle, and so that's also kind of like a boundary that you experience. And so that's kind of one thing I was talking about. It's Saint Bernard's principle doesn't always. You have to kind of apply it, but as kind of it's not an end all be all. And so there's other factors like the geometry that might have a bigger effect as well. Yeah. And so for the plate with the hole, you see stress that's concentrated on the hole. And that's a much bigger effect based on the geometry. Yeah. Thanks. Have a good day. Have a good weekend.
Yeah, Professor, I thought that was a good question. Wait, so why does the stress concentrate on the hole there on the plate?
Oh yeah, it's a good question, because the hole technically is, it is far away from the boundaries as well, right? And so the hole it's a geometrical effect. And so what you'll see sometimes that those kind of geometrical effects will kind of override what Saint Bernard's principle is telling you. Okay. But specifically for that one, the hole itself, you can kind of think of it as another boundary. Okay. Even though we're not explicitly placing a load or a constraint there, there's technically always going to be a boundary condition in those, and it's basically a stress-free boundary condition. We're not applying. Okay. And so anytime you have kind of a boundary like that in your geometry, then you're going to have some kind of interesting behavior.
Okay.
But for the,
So, because like,
oh.
okay, sorry, I have another question. So when you say like it's a stress-free boundary, I think Dr. Park kind of explained it in our strength materials class when he asked us like an oral question. So technically that since there's no material there, you can say that there's no stress there because there's no force that can act on the air. So
Yes.
is that why you have those weird super high forces that appear right there at the top and the bottom of the circle?
Exactly, yes,
Okay.
yes, yeah, because there's nothing that's kind of supporting it from the inside, because it's stress-free, then the stress has to concentrate on that area in order to maintain equilibrium. It's kind of like a backward, kind of a non-intuitive thing. And so you have your plate with the hole here, and we know that inside the surface, it's kind of stress-free. And so one way to kind of view stress-free is that there's nothing that's supporting it on this side here.
Okay.
But meanwhile, the whole plate is trying to maintain or support this stress over here, and then also kind of a fixed support on this side.
Okay.
And so, if you compare kind of this area here to kind of this area right here, right? And so compared to this, right? If we consider this point kind of has a support of all the material that's kind of down here and all the material up here.
Yeah.
Right? And so that's why the stress here isn't that big. But if we consider a point right here, because this is a stress-free boundary condition down here, you actually don't have any kind of supports down here to kind of help distribute that load.
Okay.
And so in order for this point right here, this specific point to be in static equilibrium, like if we slice this material like this.
The internal stress has to be relatively high compared to everything else.
Exactly.
Okay.
Yes.
Oh, that makes sense. Alrighty, thanks, Professor.
Yep.
Oh, and then I'm gonna start doing that, the biomechanics homework. So I know we don't have office hours on Monday, so if I have any trouble, what should I just either email you over the weekend or just come in on Tuesday?
Yeah, you can email me over the
Because
weekend.
I don't like cutting it so close, like coming in the day before it's due usually. But
Yeah. So I mean, Monday's a day off, but I'll be just be home. I'll be chilling. So if you
Okay.
if you send me an email, then I can answer you.
Okay, cool. Thanks, Professor.
Yep.
See you next week.
See ya. Have a good weekend.
You too.
Quick question on
Yeah.
the homework. So
Mhm.
when I was doing the homework, you asked to compute the ratio of the number of elements between the original activity and
Yep.
the So my question is, why doesn't it double when you take half of the original?
That's a great question. Jacob actually asked this question on Monday. And so, what you're setting when you're setting the mesh size, and so, let's say that this is the, I'm not going to draw the pole because I'm lazy. Right? And so here's all your elements, right? Okay. And so let's consider just one element right here. Okay. So here's just this one element. Okay. And so what you're setting inside ANSYS is you're setting the length of this edge right here. Right? Right. And so when you say that the edge size has to be 5 millimeters, that says that this square has to be 5 by 5. And so if you cut this in half, so you make this kind of L divided by 2, you can see here that the size of the square didn't just cut in half. It reduced by a factor of 4, right? Because it's because you're doing both sides of the square. Yeah, so there's actually a squared relationship. And so, what you should see is that it is not exact, but you should see that when you have the number of size of the element, you end up with about 4 times the amount of that. Because it's a squared relationship. Because it's
Something wrong with my calculations. Got about 3 times.
yeah, it's roughly, it's going to be somewhere between, 4 is kind of the upper bound, and it's going to be somewhere kind of in between that. But it's not 2, and that's what I
Okay.
Yeah.
I got 3.68.
Yeah.
So
Yeah. So it's something. It's going to be something closer to 4 rather than 2.
Okay.
Yeah.
All right, thank you.
Yeah.
Sorry, I have one more thing.
Sure.
So I think I just like started taking screenshots after a while without reading the directions on and I think, did you ask for the equivalent stress and the deformation, right?
Yes.
On a couple of them, I think I screenshotted the maximum stress. Should I just go delete them and retake the equivalent stress?
Yeah, if you could,
screenshots?
that would be great. Just so it's kind of uniform for
Yeah.
everyone's. Yeah.
Alrighty, and then I have one thing.
I'll think about it and I'll email.
Okay, yeah, just send me an email.
Thanks, Professor.
Okay.
It's not a content related information, I just want to be able to say.
Hi.
Oh, hey. Nice to meet you. Yeah.
So, no, it's been the entire summer kind of break.
I know. How you been?
It's been busy. So actually, so I'm working on as a medical device engineer.
That's right.
Yeah. So it's been a crazy transition from like Edwards now to involved in neurovascular stuff.
Uh-huh.
So quite the load. So right now I'm like trying to deliver a European project,
Ooh.
and it's quite a lot. So and at the same time, I was actually going to talk to you about different things I can kind of dip in because I'm doing research for Dr. Stu and kind of
Okay.
continue that on.
Nice.
And then at the same time, I wanted to talk to you about I'm taking 410 and I'm taking 540.
Yeah.
At the same time right now.
Yeah.
Now because there's a lot of crossover, I was going to be able to. My thinking was because I want to be able to do a lot of my time dedicated to research in the next year, is be able to knock off some of those electives and complete all of the required graduate components, and then have that time to be able to perhaps publish.
Sure.
And so that was my line of thinking, and so that's what I was just messing about it.
Okay.
So
Yeah, I mean it's you're gonna see a lot of the same content, and so my biggest concern would be it kind of feels like almost like a waste of a class just because it's you have a limited amount of time here, and if you take two of kind of the same thing, it's it kind of robs you of learning maybe something new. And so I won't stop you from doing that. I think your motivations are fine. I think if you're going to use that time to dedicate more to your research with Dr. Sue, I think that's a good use of it. But yeah, just be aware it's going to be a lot of the same stuff.
right. I was thinking about doing two completely different projects. Let's say with the for the independent projects, one on neurovascular and one on spinal and cardiovascular.
Okay.
And so two completely different applications with different series of headaches that pop up to be able to solve and all that.
Yeah. I mean, the projects are going to be different. So for this class, I was thinking of having something that's a little bit more constrained. And so, because this class is specifically supposed to be about like mechanical design. And so I need to think of a project of like, I want you guys to actually design something and actually tinker with the parameters and actually come up with an optimal plan. For 410, it's a little bit more free form because that's the undergrad one.
Okay.
And so for that one, a lot of the students they're coming in from like the senior design project, or they're coming in from like one of their legacy projects, like the formula team or the Baja team.
Right.
And so they already have something that they already want to apply finite elements to. And so I kind of just let them do that for the final project. But since this is a little bit different, I want to have it be more constricted. So I think probably something you're thinking would be good for the 410 project.
Okay.
But the 540 project will be.
Got it. Okay. Understood. So yeah, it's something I have envisioned and I'm trying to plan out for the next year and a half. And so yeah, definitely. I'm glad I'm taking you for both. So it makes it honestly. Along with that, I was actually going to talk to you. I'm not sure if the recording is still going.
Oh, it is. I know Anthony asked a question too.
Oh, okay.
Or let me.
Okay, yeah, you can attempt it.
Yeah, so Anthony, let's see. Do I know any good resource to find out the stress various bones experience? I don't actually, and so yeah, that I'm not really sure. I would start with just Google Scholar. I mean that's always where I start, and so you can look at like lab tests of like probably a good place to look would be maybe like some sports medicine, sports medicine journals. Yeah, like PubMed or something like that. I'm sure there's been a lot of tests that test out, like what are the loads that are experienced on like the thigh bones or something like that for like a running back or like a basketball player that's going. So yeah, I would start there, and then if it's if you can't find anything else, then maybe try broaden your search. But yeah, I don't have a good experience on that. Yeah, same here. Google Scholar is it's funny, when I was in grad school, they taught me about all these different repositories, but then Google Scholar just beats all of them. So you find everything on Google Scholar. Yeah. So what were you asked to? Oh yeah, okay, sure. All right, I'm gonna sign off, guys. So I'll see you guys next week.